At the beginning of the 20th century, we have two radical new ideas which represent modern physics, and some other things that represent modern physics, but primarily it was Planck's quantum idea about 1901 and Einstein's relativity in 1905 that were the beginning of modern physics. And today we're going to talk about the special relativity. And all of Einstein's theory is based upon these two postulates. This first one is actually known as Galilean relativity. And it says that you cannot know in an absolute sense what your motion is, as long as it is uniform motion, that is constant velocity motion. That when you are riding in an airplane, you cannot tell if you are moving or sitting still or how fast you are moving. And indeed, you are in fact sitting still relative to the airplane, and you're moving at some speed relative to the Earth, and you are moving at some speed relative to the center of the galaxy. But all of those are correct, and you cannot choose one of them as the definitive measure of motion. It's always relative to what you've chosen as your frame of reference. The second one is Einstein's contribution. That is, that the speed of light does not depend upon the motion of the source of the light or the motion of the measurer of the light. And this one is the weird one, and it leads to all the weirdness that follows. So here you have a rocket going towards the Earth, or is it in fact the Earth that's going towards the rocket? Or are in fact both of them moving at some speed relative to something else? And the answer is yes. Here you have a woman who is watching a car, and she sees the car going past at 25 miles per hour. That's the speed of the car relative to this woman's reference frame. And she sees a horse running away from her at 40 miles per hour. So the question is, how fast does the man in the car see the horse going? And I hope you can believe that he would see the horse going at 15 miles per hour. And the question is the horse in fact going 40, or is the horse going 15? And the answer is yes. Now, this classic American hood ornament has been mounted on the front of the car, and when he pushes a button, it fires a bullet which goes away from the gun, and hence the man, at 400 miles per hour. Again, the car is going 25, the woman would see the bullet going, you got it, 425. But then the man turns on his headlights, and he sees that light going away from him at the speed of light, which is a C for keletos, I think, which means fast. The woman also sees that light going at the speed of light. She does not see it going at the speed of light plus 25. So when you get things going very fast, up close to the speed of light, then what would normally be the case breaks down. And of course, this is the application of Einstein's second postulate. We take then that invariant speed of light, and we use it to measure time. This device is not actually built, but it's a thought experiment. You would have a box with a light source in the bottom, and when that bulb went off, it would send a beam of light up to the top of the box where there is a mirror, and then the light would reflect off of the mirror and come down to a detector, and so it would go up a distance d and back down a distance d at the speed of light, and so the time that would have passed would have been the distance gone divided by the speed at which it covered that distance. We then take such a light clock and we put it on a train car with this woman again, who was looking at automobiles and horses earlier. And she sees that the time that passes between when the light bulb goes off and when it gets back is 2d divided by c. However, this feller here says that she was moving. She says, no, I'm just standing still here on the train car with this light clock next to me. But he says, no, I see your reference frame as moving. And during the time that the light went up to the top of the box, it not only went up a distance d, it went to the side a distance lowercase d. And then it came down a distance d, but it also went to the side a distance lowercase d. And so the distance that the light went would be this Pythagorean sum of capital D and lowercase d. And so the time that has passed would be that distance divided by the speed. And so you can see that these two do not agree on how much time has passed. They both agree on when the event began and when the event was over. They're in absolute agreement on when it started and when it ended. But how much time passed between those two, they do not agree upon. And this man has more time pass. He sees that less time passes for her, and the reason he sees less time passes for her is because she was moving. This then is referred to as time dilation, the slowing down of the passage of time caused by the fact that she was moving. Time for her does not go as quickly as time for him, that it took less time for that event in her frame than it did for him. And the reason it took less time for her was because she was moving. But wait a minute. Was she moving? He says she was moving. Does he have the right to decide? No. And so, in her frame of reference, she would see him as the one who was moving, that she was standing still in this train car while the earth went by her carrying this man with it. And therefore, she would also see that less time passed for him. They both see the other one as moving, and so they both see time dilation, the slowing of the passage of time, for the other. Okay, so here's all this stuff that I already talked about. An experiment was done where two atomic clocks, these are clocks that measure down to a very, very small fraction of a second, very precise. They were synchronized, so they both indicated the same time, and then one of the clocks was put in an airplane and flown, while the other clock stayed in the airport. And when this clock that flew gets back to the airport, you compare the two clocks and you find that the one that rode on the airplane has less time pass than the one that stayed in the airport. Now, that's going to be a very small effect. You've got to measure to billionths of a second to see it, but it does happen. This experiment has been repeated many times, and it always comes out exactly the way it's supposed to, that time is dilated for the one that flew in the airplane, because after all, it's moved. But wait a minute. Can we say in an absolute sense that this one moved? And the answer is no. To the clock in the airplane, they would see the airport moving around, and so this clock would be moving. That they would both see the other as moving, and they would both recognize, not just see, but recognize that less time is passing for the other clock. And yet, when we bring them back together, only one clock has the time dilation effect, and that's the one that rode in the airplane. So there's a trouble. Where does the symmetry break down between these two? Why don't they both see the other as aging less? And we'll come back to that. So we have established that time is not something that moves at a constant rate, that the movement of time is determined by the movement through space. We speak of that as space-time, that the two are linked. There is not space as one idea and time as a separate idea, that they are connected as part of the same idea, which we call space-time. The faster you move through space, the slower you move through time. A related phenomenon to time dilation is length contraction. That this is a shortening of the dimension, but only the one that's parallel to the direction of travel. Notice that is bold, shouting at you, get that if this train was moving along in this direction, it would be shortened from front to back, but it would not be shortened from top to bottom or from side to side, only shortened in the direction it is traveling. Okay, let's work this out a little bit. That I'm going to measure the length of this train using its velocity. And both the people on the train would agree on how fast the Earth is moving past them, and the people on the Earth would agree on how fast the train. They would both see the same velocity. They would disagree on who had it. And so now we make a mark at the front of the train, and we see how long it takes for the train to get past the mark. And we take that time and multiply it times the velocity, and that would be how long the train was. But because time is dilated, less time passes because the train is moving, then that would mean there was less length because the train was moving. And again, the people on the train say the Earth is moving, and they would see less time passing on the Earth, and they would say that those distances on the Earth have been length contracted. They both see the other moving, they both see the other length contracted. Here is another, that airport flying the clocks around in the planes has been done many times. This is another experiment that has been done. It involves muons, which are subatomic particles with half-lives of about 2 microseconds. Every 2 microseconds, half the muon population decays. They are created in high-energy collisions in the upper atmosphere, and they are typically trapped because these cosmic particles are going so fast, very nearly the speed of light. The particles coming off of the collision are also going at almost the speed of light. And at that speed, you would travel about 600 meters in 2 microseconds. And so we put a muon detector up high in the atmosphere, and at 9,000 meters, it's finding that there are 100 million muons per second striking the detector every second. So if you went 600 meters lower, with the assumption that they are only made in the upper atmosphere in these collisions, then that population that was there at 9,000 meters, 600 meters lower, it would be half as big. And another 600 meters down, it would have again, and so forth. Every 600 meters you go lower, it would have and have and have. I think it takes 15 halvings to get down to sea level, where there should be about 3,000 muons per second hitting this detector. And when they looked at their counter at the Earth's surface, there were in fact 37 million, not 3,000, 37 million muons per second hitting the detector. So how do so many muons make it down? How do they take a trip that takes 15 half-lives and apparently only do it in 1.44 half-lives? And the answer, of course, is time dilation. Because they are traveling so fast, they don't age as quickly. Instead of what we would see as taking 2 microseconds only lasts for a little bit more than a tenth of a microsecond for the muons. Time has slowed down. The muons, of course, don't celebrate it because they're not aware that they're moving. They see the Earth coming towards them very fast, so the Earth is the one that's moving. It has the time dilation, but it also has the length contraction. And so that distance that we thought was 9,000 meters up from the Earth's surface gets length contracted to 847 meters. An extreme length contraction because we're going extremely fast towards the muons. And so that's why it only takes them about 1.5 half-lives, because they can go 600 meters in a half-life. So the muons understand it, we understand it, and it all has to do with relativity. While we're on this, let's talk about the slight effect you get. That this is, I'm not holding you responsible for this equation, this is called a Lorentz transformation, and it is used for figuring out times in a relativistic conditions. That this fraction of how fast you're going to the speed of light has to get pretty far away from 0 before the times seem to be different. That if this was half the speed of light, then if you wanted this time here to be half as big as that is, you wanted this to be this to be half as big as that is, you want this to be equal to 2, then we've got to make this the square root of 1/4. This fraction here has to be 3/4. That is, this has to be going, I don't know, really fast. That should be, oh yeah, it's going to be squared. So if you take this number and square it, you get 0.75 c. And that becomes then 1 minus 0.75 gets you 1/4, and the square root of that is 1/2. And when you divide by 1/2, you get a 2 here. So the time passed for the mover is half as big as the time passed for the person who's not moving. At any rate, pretty gold-earned fast in order to get half the time to pass. That if you want it to be different, just instead of half the time to pass, just get 99% of the time to pass, that is a 1% reduction, then you need to be going at about 1/7 the speed of light, which is still real fast. The fastest airplanes we have go at about 9.6 times the speed of sound. We call that Mach 9.6. But at that speed, the pilot would only age by this many seconds, while those of us who were not moving would age by 100 seconds. So you can see it becomes immeasurably small at the kind of speeds that we deal with in our lives. Similar, there is a formula for doing velocity, and I need to impress upon you that adding velocities doesn't work like it ought to. I won't even try to plug numbers into this. I did plug numbers in to get these results, but if these two rocket ships were each moving at 0.6 the speed of light relative to the Earth, then this rocket ship would see that rocket ship going at 0.88 the speed of light. It is not going to see, if you take 0.6 and 0.6 and add them, you get 1.2 the speed of light. But never is it seen that something is going faster than the speed of light. It just doesn't add up right. 0.6 plus 0.6 equals 0.88. If this rocket was going along and it had a missile on the front and it launched that missile away at 0.2 the speed of light, and the rocket was going at 0.9 the speed of light, then the missile would, both of these would be relative. Well, this would be relative to the rocket. this would be relative to the Earth, and what we would see from the Earth would be that the missile was going at 0.93, the speed of light. 0.9 plus 0.2 equals 0.93. It's just a crazy place, that relativistic place. And now we move on to something else. That things which happen at the same time don't happen at the same time. That if these two hands were clapping at the same moment in this reference frame, that somebody else who saw that reference frame moving would say they didn't happen at the same time. That's not just a matter of perception. They don't happen at the same time in her reference frame. And the one that happens first is the one at the back of the motion. Again, that's emphasized. Get that it is the one at the back that happens first. And it doesn't matter where she stands. She could stand in between the two, and she would see the one at the back of the motion happen first. She could be standing over here, and she would see the one at the back of the motion happening first. And it does happen first. It's not just perception, it really is reality. So it's not the one that's furthest from her that happens first. It is the one at the back of the motion that happens first, if it was simultaneous in that other reference frame. And I want to convince you that that is true. So to convince you, we have this experiment, which has got to work just right. I have an observer in the Earth frame, and I have an observer in the bus frame. And if you play your cards right, two lightning bolts will come down and simultaneously strike the bus and the platform, leaving scorch marks, and they do it simultaneous. Well, it's simultaneous for this guy in his reference frame. They happened at the same time. And the reason he knows they were simultaneous is he luckily was standing halfway in between. And the information that the lightning has hit travels to him from the two places where it hits, and it gets to him at the same moment, since it's going the same distance at the speed of light in both cases. He must assume they happened at the same time. If he was not standing halfway in between, if he was standing at some other location, he would have to do some mathematics to correct for the shorter distance one had to go and the longer distance the other. But he would come to the same conclusion. Now, this man on the bus is also located on the bus halfway in between the two scorch marks on the bus. So he is halfway in between the place where the lightning strikes. But he's on a moving bus. So while the information of the lightning strike was traveling to him, this information was traveling to him, which takes some time, maybe a very short time, but it does take some time, the bus was carrying him forward. And so it is going to be the case that he is going to get the information from this end of the bus, the front of the bus first, and from the back of the bus second. He knows he is standing halfway in between where the two lightning strikes occurred. And so, if he sees one happen first and the other happen second, it is reality that one happened first and the other happened second. So an event which was simultaneous in the Earth frame is not simultaneous in this frame, which is moving relative to the Earth. Remember that it's the event at the back that happened first. Does this person see the event at the back happening first? And you really ought to take some time and sort that out. Was it the correct one that happened first? Okay, now two paradoxes, which I believe were developed by Albert Einstein to help people with their bad thinking. So we're going to cure you of bad thinking. The first is called the twin paradox, and I have chosen to let these twins be named Homer and Ulysses. But they are twins. They were born of the same mother within minutes, if not seconds, of one another. They are the same age. And then Ulysses gets on a rocket ship and flies away from the Earth at a constant velocity, and Homer stays on Earth. And they communicate with one another, talking about what's going on and how old they are and how many birthdays they've had. And they both see the other as moving. Homer sees Ulysses as moving in the rocket. Ulysses sees Homer as moving on the Earth. And they are both correct. They are both moving in those different reference frames. And as a consequence, they both correctly see the other one as aging less. Both of them see each other aging less. And that's crazy. Doesn't seem possible that these two could both be younger than each other. But they are. You say, Mr. Houghton, you got to put those people back together. We got to stand them side by side. I want to see what it looks like for two people standing by side to both be younger than each other. To both not have a beard when I have a beard. The answer, when you bring them back together, is that it is Rocket Man Ulysses who is younger. When you stand them side by side, the one who rode in the rocket is younger. And yet, I stand by my statement that they are both younger than each other while the rocket trip is going on. But what about when you stand them side by side? It ends up being Ulysses, the traveler, who has aged less. But why doesn't he say that Homer is a traveler who aged less? He is. He was going at just the same velocity as Ulysses was going. Well, the problem is resolved when you realize that they are not doing exactly the same thing. While Ulysses was traveling with a constant velocity, Homer also had a constant velocity. But when you decide to bring them together again, Ulysses has to turn around and come back. And that is accelerated motion. It is not constant velocity, and it is absolute. We can say definitively that it is Ulysses who accelerates. Homer does not accelerate. And it is during that acceleration that Ulysses' age comes to be permanently different than Homer's. And that, of course, is also the resolution of the problem of the clocks. That actually both of the clocks were accelerating because they were on a spinning Earth and they were in a gravitational field, but the one on the airplane accelerated more. And that's why less time passed for it. As I said, gravitational fields also create accelerating frame of reference. And if we did not take into account the effect that accelerating frames have on the passage of time, then GPS would not work. Absolutely would not work. That you could not use your GPS to find your way or where you were. It would not work. That this relativity stuff is real, and it needs to be taken into account when you do GPS. That accelerating frames of reference actually do not belong in a lecture on special relativity. They are part of general relativity, where you do study gravity, accelerating frames of reference. That's where the warped space-time happens. That's where E equals mc squared occurs, is in general relativity. But we need to talk a little bit about this because it's part of the Virginia SOLs. That what this statement says is that energy and mass are equal. And this is just a great big constant of proportionality. But all year long we've been talking about energy being conserved and matter being conserved, but in fact they are not. That you can change matter into energy and vice versa. That in an atomic bomb or an atomic reaction, matter is destroyed and energy is created from it. And when you move things fast, like in a particle accelerator, that kinetic energy manifests itself as greater mass. To have more energy is to have more mass. And if the particle accelerator folks didn't take that into account, their particle accelerators would not work. That the mass goes up significantly, and it must be accounted for. Further, because of this statement, you can see that to travel at the speed of light, to have kinetic energy represented by a massive object going at the speed of light, would mean for it to have infinite energy and infinite mass. So we cannot take massive things like human beings and make them go the speed of light, let alone faster than the speed of light, which I know is your heart's desire. Last problem, and this is called the train robber paradox, that this evil robber has rigged up both ends of this tunnel with doors that he can trap things inside and rob them, and this train is traveling down the track at a relativistic speed. The train is longer than the tunnel is, but this evil genius realizes that because it's traveling so fast, it will be length contracted, and so it will fit inside the tunnel. However, there are geniuses among the good guys riding on the train as well, and they realize that it's the tunnel that is moving. And so the tunnel is going to be contracted, and there's no way it's going to hold the train in. Both of them see the other as moving, both of them see length contraction, and again it seems like a paradox. They can't both be shorter than each other. And everyone is correct in their perception that the other guy is shorter. The resolution lies in simultaneity. That the train robber was closing both doors simultaneously in his frame of reference when both ends of the train were inside the tunnel in his frame of reference. But an event which was simultaneous in the tunnel frame of reference is not simultaneous in the train frame of reference, and it will be that one of these doors shuts first, and you are supposed to figure out which one it is. Thank you, and good night.